The objective of this lecture is to provide Newton's laws of motion for a particle and to demonstrate Newton's laws on examples. This lecture will be divided into the following parts. First, we will provide a definition of an inertial reference frame. Second, using the definition of an inertial reference frame, Newton's laws of motion are developed. Now, these laws include the first law, the second law, and the third law. And then a procedure is developed for using Newton's laws in solving a problem. And finally, the process is implemented on examples. So we'll start with the definition of an inertial reference frame. Now, up till now, with regard to kinematics, we have not discussed the nature of a reference frame other than to say what is a reference frame. We haven't actually described anything special about any of these frames. Reference frames all rotate and translate relative to one another. But in order to apply the laws of mechanics, we need to tie everything to a particular reference frame, and that reference frame is what's called an inertial reference frame. So in order to define an inertial reference frame, we're going to start as follows. Consider a collection of particles. Now, this is just some collection of particles. It doesn't have any particular structure to it. But what's important about these particles is that they all have mass. So that they each have some mass. And furthermore, we are going to consider motion relative to a frame A. So motion of these particles relative to a reference frame A. Now, this is how an inertial reference frame is actually defined. So far, we haven't said anything about inertial reference frames. We just have a reference frame A. So in order to make a frame inertial, or in order to understand what an inertial reference frame is, let's now assign some type of motion to these particles. So what we're going to say is assume that every particle in the collection is subject to zero force. And that's important because that's how we start. Kinetics always starts with an action, right? And an action that's applied to a particle is a force. It's the only action that can be applied to a particle. So the action is is that thing that initiates motion. So here we're going to assume that every particle in this collection is subject to zero force. So then, if the relative acceleration between any two zero force particles Q and P is itself zero as viewed by an observer fixed in reference frame A, then the reference frame A is inertial. So we can say that in a slightly more mathematical way as follows, which is given any two zero force particles Q and P, if the acceleration of P relative to Q in reference frame A is equal to 0, that implies that A is an inertial reference frame. So that's how an inertial reference frame is defined, is that we start with this concept of action. And if it turns out that there's no force being applied to any two particles, doesn't matter what these particles are, as long as there's no force being applied to them, if we just pull two zero force particles at random, and we ask the question, is the acceleration, the relative acceleration between these two particles, 0? If the answer is yes for all such particles, then the frame relative to which that motion is being observed, which is the relative acceleration between these two particles, that frame A is an inertial reference frame. Now, from this point forth, we're not going to use the terminology A for a reference frame if it's inertial. We're going to use the terminology I. So that's going to come up in the next, in what follows. So we will use the following terminology or notation for an inertial reference frame, which is that an inertial reference frame is denoted I. So by the symbol I. Makes sense. I, inertial. So that's how we do it. Now, using an inertial reference frame, we can now develop Newton's laws. And this is for a particle. So there are three laws. Newton's first law. So Newton's first law is stated as follows. An object will move with zero acceleration relative to an inertial reference frame unless a non-zero force is applied to the object. And that's kind of a statement of what we already said, right? We already said that if we're standing in an inertial reference frame and the relative acceleration between any two zero force particles is 0, then the only way that can happen is if we're standing in an inertial reference frame. If that reference frame weren't inertial, then if we're observing relative acceleration motion of particles that have no force being applied to them, then there's no way that frame can be inertial if the acceleration is zero for all such particles. So this is basically a restatement of that. It just says an object will move with zero acceleration relative to an inertial reference frame unless a non-zero force is applied to the object. So now we go to Newton's second law. Now, Newton's second law is probably the one that people are most familiar with, but it's worth restating here, which is let F be the resultant force applied to a particle P of mass m, then the force is related to the inertial acceleration of the particle as F is equal to the mass of the particle times the acceleration of the particle in the inertial frame. So what it basically says is that if I have a force that's being applied to a particle, then that force is equal to the mass of that particle times the acceleration of that particle as viewed by an observer in an inertial reference frame. So finally, we have Newton's third law. Now, Newton's third law is stated in different ways depending upon where you see it. But one way of stating it is if a particle exerts a force on another particle, then the other particle exerts a force of the same magnitude but in the opposite direction from the force exerted by the first particle on the second particle. So another way of looking at this is as follows. So if we're given two particles, given particles Q and P, if FQP, the way I've written it, is the force exerted by Q on P, then minus FQP is the force exerted by P on Q. That's Newton's third law. It's also a statement of what's called action and reaction, and you'll actually see it written that way at times, which it'll read as follows. For every action, there exists equal and opposite reaction. And that's exactly the situation that you see here, which is that the force exerted by Q on P is an action. It's the force that the particle P is exerting on the particle Q, and particle P reacts by exerting a force with the same magnitude but in the opposite direction to Q as Q exerts on P. So those are Newton's three laws. Now the next part is using Newton's laws to solve a problem, whatever that problem happens to be. So we'll start again with Newton's second law. So from Newton's second law, we have that the force is equal to the mass times the inertial acceleration of the particle. Now, we can see that there are different things on each side of this equation, which is on the left-hand side of this equation is the force. And the force corresponds to the kinetics. The right-hand side contains the acceleration, and that is the kinematics. Now, you can see that in order then to be able to solve a problem, we need to do both kinematics and kinetics. And each one of these pieces then comes together to be able to apply Newton's second law. And ultimately, what we're interested in is because the system moves, the goal is to describe the motion. And in the case of mechanics, this motion is described via a system of differential equations. In other words, the differential equations are the equations that once we've derived them describe the motion of the system. Note that the differential equations don't tell us what the actual motion is. They just tell us the equations that if we could solve them would give us the actual motion. So we're starting with this first step of wanting to describe the motion, and that description is given through differential equations. So the process for being able to solve these differential equations or determine these differential equations is as follows, is that we need to do kinematics and kinetics. So the first step is we have to do kinematics. And of course, we've studied kinematics previously, and what we have to do is we have to develop the following pieces, which are reference frames, and coordinate systems. And of course, one of those reference frames has to now be an inertial reference frame because the laws of mechanics are only valid in an inertial reference frame. So we have reference frames and coordinate systems, and then we ultimately want to determine the inertial acceleration of the particle and once we've determined the inertial acceleration, we now have the kinematics complete, so we have the right-hand side of Newton's second law. So the next part is to do the kinetics. And the kinetics is generally broken up into the following pieces, which are first, we draw a free body diagram. And then we quantify all the forces in that free body diagram. So we quantify all forces. And then, using that quantification of the forces, the third step is to apply F equals MAPI. Of course, that's Newton's second law. And these are the sort of broader steps, but within each step, we have to be very careful and make sure that we've determined everything exactly correctly in order to be able to set these two things equal to each other, the force and then the mass times the inertial acceleration. So the easiest way to be able to do this is via example. It's easier to explain what's going on when you actually see how it plays out in a few problems, which is what we're going to do now. We're going to do a few examples of applying Newton's second law. So here's the first example. Now in this problem, we're given a particle of mass m, which is suspended from a rigid massless arm. So here's my particle, which is P, and it's got mass m. And it's suspended from a rigid massless arm, which is hinged at a point which I'm going to call O. And that hinge is actually fixed to the ground. And the angle formed between the vertically downward direction and the arm is the angle theta. And I'm going to assume that gravity, which is the local acceleration due to gravity, acts in that same direction, vertically downward. And the objective is to determine the differential equation of motion for this system. Now, it's a rigid massless arm of length L. Now, what's important here, and this is very important, is that we have to determine an inertial frame. So implicitly, what winds up happening is we have to make an approximation, because there's no such thing as an actual inertial frame, because we could never actually find such a frame in reality. So we assume that something is good enough to be an inertial frame. And that's exactly what we have here, which is that we have this ground, and we're going to assume the ground is an inertial frame. So I'm going to write that at the beginning here because it's just easier to know what we're dealing with as far as an inertial frame when you're actually starting to use Newton's laws. So we're going to assume the ground is an inertial reference frame. Okay. Now, given that we've done that, let's take a look and see what we need in order to determine the differential equation. So that's the goal here. So the objective is determine the differential equation of motion for the particle in terms of the angle theta. So now let's go ahead and let's start solving this problem. So as I said, we need to do the kinematics and we need to do the kinetics. So we're going to start by doing the kinematics. So the kinematics in this case, if we actually look, you'll actually see that there's one rotation. So that implies that there are two reference frames. Now, without getting into a lot of details here, because we've done so many kinematics problems at this point, we're going to go through the kinematics a little more quickly than we would normally go through them. So these two frames are the ground, and that's the base reference frame. And it's not only the base reference frame, it's actually the inertial frame in this case, because I said the ground is an inertial frame. And then we have the arm, which is the rotating frame. So remember, when we do kinematics, we work our way backward from the last frame to the first. So let's pick coordinate systems that are fixed in each of these frames, starting from the arm and then going to the ground. So A is equal to the arm, And the coordinate system that's going to be fixed to the arm is going to have its origin at O. I'm going to put ER along OP. EZ is going to be out of the page. And then E theta is equal to EZ crossed with ER. And then G is equal to the ground. And I'm going to put the origin again at O because O is fixed to both the arm and the ground. And then I'm going to put the coordinate system or the basis, EX, EY, EZ. That's going to equal ER, E theta, EZ when theta equals 0. So now that picture, of course, is fairly straightforward. It's not an incredibly complicated picture, but let's draw it anyway. So here's EX, here's EY, EZ is out of the page. This direction, which is along the arm, is ER. This direction is E theta, and the angle is theta. So that's our picture. Now, given this picture and given the way we've defined the coordinates, the position of P relative to O is equal to LER. Now, it's really important. I'm going to put this over here because it's really important, is that all distances have to be measured from an inertially fixed point. Otherwise, you cannot apply Newton's laws. So all distances must be measured from an inertially fixed point. What that means is that the point from which you're measuring all your distances has to be fixed in the inertial frame. And in this case, O is fixed in the inertial frame. So as a result, we're going to measure from O, which is why I have the position of P relative to O. And then from here, we can just compute the velocity, the inertial velocity and the inertial acceleration. So then, the velocity of point P as viewed by an observer fixed to the ground is the rate of change in the ground of the position of P relative to O, which is equal to the rate of change in frame A of the position of P relative to O plus the angular velocity of A and G crossed with the position of P relative to O. Now, if we look back on that position was equal to L times ER. So the rate of change in frame A of the position of P relative to O is 0 because L is constant and ER is fixed in the arm. The second term is the angular velocity of A and G crossed with the position of P relative to O, which is equal to theta dot EZ, that's the angular velocity of A and G, crossed with LER, which is equal to L theta dot E sub theta, from which we obtain that the velocity of point P as viewed by an observer fixed to the ground is L theta dot E theta. Then we can use the velocity as viewed by an observer fixed to the ground to get the acceleration of point P as viewed by an observer fixed to the ground. Well, that acceleration is the rate of change in the ground of the velocity of point P as viewed by an observer fixed to the ground, which again, that velocity of P as viewed by an observer fixed to the ground is expressed in coordinates fixed in frame A. So this is d dt in A of the velocity of point P in G plus the angular velocity of A in G crossed with the velocity of point P in G. So now we can compute all these quantities, but in this case I'm going to go a little bit more directly to the final result, which is that d dt in A of the velocity of point P as viewed by an observer fixed to the ground is equal to L theta double dot E theta. Because L is constant, E theta is fixed in the arm, so the only thing that changes is theta dot, which gives me theta double dot. And I get the second term is plus theta dot EZ crossed with L theta dot E theta, which gives me L theta double dot E theta, and then EZ crossed with E theta is minus ER. So I get minus L theta dot squared ER, which then implies that the acceleration of P and G is minus L theta dot squared ER plus L theta double dot E sub theta. So that takes us to the end of the kinematics part of this problem, and now we can move on to doing the kinetics. So now we do the kinetics. So here we have the first step in the kinetics is the free body diagram. So what are the forces that are acting on this particle? Well, there are two forces. There's the force of gravity, which is mg, and then there's a reaction force, or a force exerted by the arm. I'm going to call that force R. So let's label what these are. So mg is the force of gravity. And then R is the force exerted by the arm on the particle. Now, the force exerted by the arm on the particle has to be along the arm. So I'm going to write that here. This is along the arm. So from this, we actually get the following, which is the force of gravity is in the vertically downward direction, but the vertically downward direction is Ex. So that's mg times Ex. The force exerted by the arm is along the arm, so it's in the direction Er. Now, it sometimes gets a little bit confusing when you're dealing with unknown forces, because the force exerted by the arm is unknown, to whether to put it one direction or whether to put it the other direction. And it turns out that it doesn't matter because you don't know what it is. So as a result, that scalar R that's multiplying ER could be positive or negative, and I don't know ahead of time which one it is. So I just arbitrarily just call it positive, and if it turns out that it's in the wrong direction, it'll come out in the algebra. So I don't need to worry about that. Now, given that these two are the forces, we have that the force, the resultant force, is equal to mg plus R, which is equal to mg Ex plus R ER. And this force has to equal the mass times the inertial acceleration, which in this case is the acceleration as viewed by an observer fixed to the ground. So as a result, we wind up with mg Ex plus RER is equal to m times minus L theta dot squared ER plus L theta double dot E theta, using the acceleration as viewed by an observer fixed to the ground from the kinematics step. Now, you'll notice that in this particular expression, we have some terms given in some quantities given in terms of ER and E theta, and we also have some quantities given in terms of Ex and Ey, and in particular, we have this one term mg Ex. So what we need to do is we need to figure out which coordinate system should we use to solve this problem. Should we use the basis that's fixed in the arm, or should we use the basis that's fixed to the ground? And it turns out that for this problem, it's much more convenient to use the basis that's fixed in the arm. So we need to transform Ex to the basis ER E theta Ez. So recall that the diagram I had from earlier is this diagram, which is this direction was Ex, this direction was Ey, this direction is Ez, and then ER was this direction, and E theta was finally in the direction as drawn. So we can see that from this diagram, Ex can now be solved for in terms of ER and E theta. which is it's equal to cosine of theta ER minus the sine of theta times E theta, because this direction right here is negative E theta. So EX lies between ER and negative E theta. So therefore, we have that the force is mg times EX, but EX is cosine of theta ER minus the sine of theta E theta. And then we have plus RER, and that has to equal the mass times minus L theta dot squared ER plus L theta double dot E theta. So now we can equate components, and that gives us the following two equations. If I take the ER component, I've got mg cosine of theta plus R is equal to minus ML theta dot squared. That's the first equation. The second equation gives me minus mg times the sine of theta is equal to ML theta double dot. Now, in this particular problem, there's only 1 degree of freedom because there's only one variable in the problem. So there's going to only be one differential equation. And you can see the differential equation is right here. So this is the differential equation. And in this particular case, it turned out to be fairly simple just because there's not a lot going on motion-wise in this problem. But that winds up being the differential equation, which if I rearrange that differential equation, which I can do, I wind up getting that I can put everything on one side and I can set the whole thing equal to 0, and I wind up getting the following result. So this result is that ML theta double dot plus mg times the sine of theta is equal to 0, from which I can actually divide through by ml to get theta double dot by itself. So I get theta double dot plus g over L times the sine of theta is equal to 0, and that is the differential equation. So we've set out to determine the differential equation, and now we've determined it, so we're done solving this problem, which is the objective was to get the differential equation of motion in terms of the angle theta, and now we have the differential equation of motion in terms of the angle theta. So we're finished with this example, and we can move on now to another problem. So now let's consider the following example. We have a tube that rotates relative to the ground. So this tube is such, and it rotates with an angular velocity, which I'm going to denote as capital omega, and it's hinged at this point O, which is fixed to the ground. And inside this tube is a particle of mass m, and this particle slides inside the tube. And the particle is subject to a viscous friction force at the point of contact between the tube and the particle. And we're going to assume in this problem no gravity. So assume no gravity. So this is kind of like something working or moving in the horizontal plane. So there's no gravity in this problem. And we want to determine the differential equation of motion. So the objective is to determine the differential equation of motion. But before I do that, let's just mark one other thing, which is that the distance from O to P is going to be denoted R. So in this objective, which is to determine the differential equation, we're going to determine the differential equation of motion for the particle in terms of R. Now, in order to make this a little bit easier, we're going to assume that the angular velocity omega is fixed in the ground, which means its rate of change in the ground is 0. And we're also, just like we did in the previous problem, we're going to take the ground to be the inertial frame in this problem. So G is the inertial frame. So you can see that we have a setup here that's not exactly the same as what we had in the previous problem, but it has some similarities there. There's one rotation. So we're going to go through this problem in a similar way, at least for starters, and then we'll go through the rest of the kinematics. So there's one rotation, which is that angular velocity, omega, which implies we have two reference frames. These two reference frames are the base frame, which is the ground, and that, as I said, is the inertial frame, and then T is the tube, and the tube rotates relative to the ground. So given that the tube is the last frame, we will start with coordinates fixed in the tube and work our way backwards, as we always do, which is the origin of this coordinate system is at O. I'm going to put UR along OP. UZ is out of the page, and then U theta is equal to UZ crossed with UR. And then I have the ground, which is my inertial frame, and the origin of this coordinate system is again at point O, because that point is fixed to the ground. And then I'm going to put the following basis. Now this is a little different from the way we did it in the previous problem, and it has to do with the fact that we're given an angular velocity and not given an angle. This is equal to UR, U theta, UZ when T equals 0, not when theta equals 0, because I don't have any angle theta in this problem. So I can't say when theta equals 0. But when T equals 0, I freeze the coordinates UR, U theta, UZ, that basis. I freeze it at time T equals 0, and those three directions are what I'm defining as EX, EY, EZ. Now once we have the setup, we can actually get that the position of P relative to O is equal to R times UR. And again, I'm going to mention this because it's really important, is that where all distances are measured from point O, because, now this is important, because O is fixed in the inertial reference frame. And in this case, that inertial reference frame is G. So now we can actually start moving through the calculations here, which is that the velocity of point P as viewed by an observer fixed in G is the rate of change in G of the position of P relative to O, which is equal to the rate of change in the tube of the position of P relative to O plus the angular velocity of the tube as viewed by an observer fixed in the inertial frame, which is the ground, crossed with the position of P relative to O. So now, in this case, we have that the rate of change in the tube of the position of P relative to O, that's equal to R dot times UR, because R is changing. And the angular velocity of the tube as viewed by an observer fixed to the ground crossed with the position of P relative to O is equal to omega crossed with R UR. Now also, omega, because the axis of rotation is UZ, is equal to omega times UZ. So that implies that omega TG crossed with the position of P relative to O is equal to omega UZ crossed with R UR, which implies that omega TG crossed with the position of P relative to O is equal to R omega U theta. Now we can add these terms together, and we get the velocity of point P as viewed by an observer fixed to the ground is equal to R dot UR plus R omega U theta. So that's the inertial velocity. Once we have the inertial velocity, we can get the inertial acceleration. So the inertial acceleration is equal to the rate of change as viewed by an observer fixed to the ground of the velocity of point P as viewed by an observer fixed to the ground. But again, this velocity is expressed in coordinates fixed in the tube. So this is the velocity of point P in the ground differentiated by an observer fixed in the tube plus the angular velocity of T in G crossed with the velocity of point P in G. So now let's get these terms separately and then we'll put them together. So d dt and t of the velocity of point P as viewed by an observer fixed to the ground is equal to r double dot ur, that's the first term, plus r dot omega u theta. But remember that omega is equal to a constant because the angular velocity vector omega is fixed in G. So as a result, we have that fact. So that means that I'm not going to differentiate when I do this product. It's r dot times omega plus r times omega dot, but omega dot is 0. So then the next term is omega tg crossed with the velocity of P in G, which is equal to omega uz crossed with r dot ur plus r omega u theta, which is equal to, well, uz crossed with ur is u theta, and uz crossed with u theta is minus ur. So if I take the vector products and then rearrange into the order of that the basis is defined, I get minus r omega squared ur plus r dot omega u sub theta. And now these two terms can be added to get the acceleration of point P as viewed by an observer fixed to the ground. So then, the acceleration of point P as viewed by an observer fixed in G, if I add the terms together, gives me r double dot minus r omega squared ur plus 2 r dot omega u sub theta. So that takes us to the end of the kinematics because we've obtained the inertial acceleration of the particle. So next we'll move on to the kinetics. So the kinetics in this problem are done as follows, which is first we're going to draw the free body diagram. And let's look at the forces that are acting on this particle. So the first force that we have acting on this particle is a reaction force or a normal force. So I'm going to call this force N. We have a friction force, and that's all we have. Those are the only two forces because there's no gravity in this problem, right? So we have to be able to figure out how to resolve these forces. Now let's write down what these are. So N is the reaction force exerted by the tube on the particle, and then F sub F is the friction force. Now, we have to realize a couple of things here. First is that the normal force N must be orthogonal to the direction along the tube. So as a result, it means that N cannot have a component along UR, because UR is the direction along the tube, which means that N has two components. It's equal to N sub theta U sub theta plus N sub Z U sub Z. So that takes care of this normal force, or this reaction force that's applied by the tube to the particle. So the next thing we need is we need the friction force. So then the friction force, well, we've got viscous friction, right? So this is equal to minus c times the velocity of point P, but it's got to be relative to the correct frame. And the frame in this case is the tube. And the reason that it's the tube is because the particle is sliding on the tube. So you can think of the tube as a curve. The curve in this case is a straight line, but the force that's being exerted due to friction is due to the fact that the particle is sliding on the tube, which is why the velocity in this viscous friction force is the velocity of P as viewed by an observer fixed in T. And we know that the velocity of P as viewed by an observer fixed in T is just equal to d dt in T of the position of P relative to O, and that's equal to r dot times UR. So that means that the friction force is equal to minus C times r dot times UR. So as a result, the force, or the resultant force, which is equal to the normal force plus the friction force, is equal to n sub theta u theta plus n sub z u z, and then minus c r dot ur. And that has to equal the mass times the inertial acceleration. So this has to equal the mass times the inertial acceleration of the particle. So now that we know that, we can actually substitute in the inertial acceleration, and we can get an expression for on both sides. We can get the kinetics and the kinematics. So that gives us n sub theta u sub theta plus n sub z uz minus cr dot ur is equal to the mass times r double dot minus r omega squared ur plus 2r dot omega u sub theta. Now, we can see that n sub theta and n sub z are unknown. And we can also see that there's no component, n has no component along UR, which is what I said earlier, right? So that means that if I take the force and I dot it with UR, because that has to equal the mass times the inertial acceleration dotted with UR, that has to be the differential equation, because there's no component of unknown force in that direction. So we can go ahead and do it, and we can see what happens. If I take F dotted with UR, I get minus C times R dot, because UR dotted with U theta is 0, and UZ dotted with U theta is also 0, and then UR dotted with UR, of course, is 1. And that has to equal M times R double dot minus R omega squared, because again, UR dotted with UR is 1, and U theta dotted with UR is 0. So this is the differential equation. So there it is. It's a differential equation. And you can see that it comes out exactly the way you would expect, because the particle is moving inside the tube, so it's sliding along the tube. So the direction of allowable motion is along the UR direction. So as a result, it has to be the case that the differential equation is going to be described by a variable that tells you motion along the allowable direction. And in this case, that allowable direction is UR, which means I get the differential equation that I have here. If I want to, I can rearrange this just to put everything again on one side and set it equal to 0, which I can do right now. So then, rearranging gives M times R double dot minus R omega squared plus CR dot is equal to 0, which if I rearrange further gives mr double dot minus m omega squared r plus CR dot is equal to 0. And if I rearrange this into the order of the derivatives from highest to lowest, I get mr double dot plus CR dot minus m omega squared r is equal to 0. And that is the differential equation. And you can see again, just like it was in the first example, it's a second order differential equation. In this case, it's in terms of r, which is what we had set out to accomplish at the beginning, which is to get a single differential equation in terms of r, because there's only one degree of freedom in this problem. So that takes us to the end of this example, and also takes us to the end of the lecture, because we've studied two examples now which were different in their form, and we've gotten a better understanding of how to apply Newton's laws to determine the equations that describe the motion of a system. So as a summary of this lecture, first, a definition was provided of an inertial reference frame. And then, using this definition, Newton's laws of motion for a particle were described. And then a process or a procedure was developed for using Newton's laws in a problem. And then fourth, the procedure and the laws themselves were studied on examples to derive the differential equations that describe the motion of a system. And that takes us to the end of this particular lecture. In the future, we will use Newton's laws to derive the differential equations of motion for other systems, but for now, we will stop this lecture here.